Okay, thank you very much for the introduction, and thank you also for the possibility to share my research with you. The research is a joint project with the Institute of Applied Mathematics, where I'm from, and Peter Krawitz, who's from the Institute of Genomic Statistics and Bioinformatics. And I want to talk to you about the power of recombination today, and I want to show you a model that includes the new parameter, the recessive gene count, and in the end I want to conclude on an argument on the emergence of complex organisms. First, here are my conflicts of interest. I have nothing to declare, and then we can start with a little bit of history on mutation rate theory. So in 1991, John Drake found negative correlation between the mutation rate per base pair and the genome size across different species. And he hypothesized that so the product of both, the genome-wide mutation rate, then would be constant among different species, a concept that later became known as Drake rules. But in the 90s, data and methods for mutation rate estimations were limited. So fast forward 20 years and we have more comprehensive data, and we know, for example, that the genome-wide mutation rate of humans, which is the red dot, differ significantly from that of E. coli, which is the blue dot. And moreover, Michael Lynch and his co-authors found that there is a negative correlation between the genome-wide mutation rate and the effective population size. So they could add this parameter of effective population size to the theory of mutation rate evolution. And moreover, they developed the drift barrier hypothesis. This hypothesis states that directional forces such as selection like to be in equilibrium with random forces such as genetic drift and natural fluctuations. So if, for example, in small populations, genetic drift is more pronounced, and therefore we would expect a higher mutation rate to compensate with this. Today, even with the ongoing process in genome sequencing, we recognize that it's maybe overly simplistic to reduce all the genetic information of a diploid individual to just one number. So therefore we developed a population dynamics model that acts more structure and includes these parameter of recessive gene count. In such a way we're able to test different hypotheses and also apply it to various different species. And in our simulations, we concentrate on complete recessive alleles, meaning that even if a gene is degenerated by a mutation, the fitness of the individual is unaffected and it's still optimal fit. Even if the individual has a lot of mutations, the fitness still is unchanged. Only when a mutation appears in a homozygous state, that is, that the individual gets excluded from the mating process. So this would correspond to classical models with a dominance coefficient of h equal to 0 and a selection coefficient of s equal to 1. If we now want to generate within this model an offspring for the next generation, we would first sort out all the affected individuals and then look among all the remaining populations uniformly at random, because now all they have the same fitness for parents to mate. And for the formation of an offspring, there are two main mechanisms that come into play. First is recombination. There, at each site, we choose uniformly and independently with equal probability R if there is a recombination site or not. And if so, we would form the gamete accordingly. Okay. And obviously, we would do this with both parents to then again get a diploid individual. And the second mechanism now is the addition of new deleterious mutations. Therefore, we would sample first a Poisson random variable with parameter 2 mu, where mu is the genome-wide mutation rate, and then choose a location uniformly at random across all the 2n possible locations that there are. Then to analyze stability of this model, we look mainly at two statistics. First is the prevalence, which is the fraction of affected individuals in the population. And second is the mutation burden, which is the average number of mutations per individual. Okay, enough theory, let's have some fun and look at some simulation results. For example, here with a recessive gene count of 600 genes, genome-wide mutation rate of 0.025, and initially without recombination, keep that in mind. And then we see that both statistics, the mutation burden and prevalence, after a short burn-in phase, fluctuate around a well-established equilibrium that we even can have analysis to calculate this equilibrium. And this looks all very stable and very predictable, and it could all go on forever. But just to check and to be sure, maybe we don't run it over for 10,000 generations, but just a couple more generations. And now you can even already imagine what happens next. Boom. We get a huge increase in the mutation burden and the prevalence far over a level that natural populations could sustain. So what happens there? To understand this metastabil phenomenon, we have to go back to our mock population and introduce yet another statistics. And therefore, we don't think of the population as a group of individuals, but rather just a bunch of gametes. And we would reorder them in such a way that in each group, individuals carry the same number of mutations. And in such a way, we can distribute the population into haploid load classes. And if we now look at these haploid load class distributions over time, then we see that also initially they're in equilibrium, but when we come to the point of the population degeneration, a whole cascade breaks loose and a lot of these haploid load classes go extinct in a short amount of time. And if we zoom in closely, we can see that it all gets triggered by the extinction of the least loaded class, so the mutation-free gamete. This concept, so the irreversible accumulation of mutations due to the extinction of the least loaded class, is known as Muller's ratchet. And now we want to examine the effect of the recessive gene count on this degeneration of the population. Therefore, we did a lot of simulations with a numerous variety of different parameters and see if there is metastabil behavior or not. So in this graph, on the grid, the size of the scattered dots represents the number of simulations that had an extinction event. For example, here in the middle, you can see for n equal to 600 and the genome-wide mutation rate of 0.025, we have the parameter combination that we looked at before in detail. And you see all of the simulations had an extinction event within 100,000 generations. So the higher the mutation rate or the higher the recessive gene count, the more likely it is that we see these extinction. And this corresponds to the size of the least loaded class. So the more mutation-free gametes there are, the less likely they are to go extinct due to natural fluctuations. Hence, species with a high mutation rate or a high recessive gene count encounter this barrier. But why would it be a drift barrier? What has it to do with randomness? To understand that, we go back to focus on just one mutation rate and look at the effect of the number of genes, so on the recessive gene count. And here we have the expectation of the haploid mutation burden, which we see increases like square root of n in equilibrium. And after the transition, so after the degeneration, of course, the mutation rate is elevated. But we don't want only to look at the expectation, but also at the variance of the haploid mutation burden, which is a measure for fluctuation. And there we see that the variance increases linearly with the recessive gene count and exceeds the expectation. So therefore, we can really refine the drift barrier hypothesis and add the recessive gene count as one parameter that affects the randomness of the population. But remember, all of this happened in the absence of recombination. So if we now switch on recombination, we see that the variance is lowered significantly, and more importantly, stability is regained. So we have no degeneration of the population anymore with recombination. Therefore, we can conclude, what can you do? We have the reason why this is the potential of recombination to reduce the number of mutations per gamete. And therefore, we can also restore the mutation-free gamete if it would go extinct due to natural fluctuations. And we can now conclude that what can you do if you're an organism and you want to solve even more complex problems, but you encounter one of these drift barriers with your parameters? Well, a solution might be to start mating and emerge a tool like recombination to ensure stability. Okay, thank you. I'm happy to ask your question.
Thank you very much. So questions for Luis?
Hello, a very nice talk. I'm Giuliana Giannuzzi, University of Milan. So in human, we know that males and females recombination happens in different positions. So females more closer to the centromere, males closer to the telomeres. Do you think this might also be important for the species? So this, could this be also influence the survival of the species?
Yeah, very interesting question. We haven't looked at that yet. So we assume that both recombination and mutation happen with equal probability across all the genomes and across all the different individuals in our population. And we know that it's not true in nature, so that's just a simplification for our model. But it would be interesting to check if it has makes a difference if we switch this up between different subgroups of the individuals. Yeah.
Thanks, thank you.
Hello, this is Jason from Mangalore, India. So my question is this the same for the smaller population and the larger populations? Does the recombination has the same effect on the maybe a founder population or an admixed population?
Yeah. Oh, sorry, I didn't want to do that. Yeah, very good question as well. So we know that the size of the population affects the fluctuation, and we see that in smaller populations the degeneration happens earlier for fewer genes and for smaller mutation rates than in larger populations. Yes, the effect of the population size is felt also in this case. Yeah.
Okay, so let's thank Luis again. Our next speaker is Juha Riikonen, and